Okay, I'm going to talk about lazy arrays, which were mentioned in a talk yesterday. Oh, it is moving on its own. Is that a thing? Okay, so I'm going to talk about two kinds of lazy arrays, push and pull arrays. These are somewhat well known in the small world of people that develop Haskell EDSLs for targeting GPUs. So if anyone else is in that group, you've probably seen them already. First, pull arrays. So what is a pull array? Right? The idea is we represent an array as a function from an index to a value. Right? So to create a pull array, we need to provide a function and we need to provide a length. Right? So we can turn a vector into a pull array by essentially creating a closure that closes over the vector and uses the index to do a vector rep into the vector. Right? And then we can turn a pull array back into a vector by using the built-in build vector function to essentially manifest the vector using this function. Okay? So we can index into the vector using this function nth pull, where we basically break open the pull array and call the function on this index. That gives us the ith element of this array, right? So if we create this pull vector here with 1, 2, 3, 4, 5, and we want the 1th element, that gives us 2, right, as you'd expect. So now here's another computation where we create our pull array A, right, and then we match on it and we create a new pull array that makes this new lambda function here. So this function takes an index. Inside here, it uses the old function to get the thing at the ith index, and then the result, it increments by 1. So if we do this, and we do the same thing, nth pull to get the first, or the 1th, whatever element, the second. Now it returns 3 instead of 2. So what did we essentially do? We mapped +1 over the function, or over the array, rather. So we can define pull map, right? What pull map does is it doesn't actually allocate a new array, right? It pushes the action of the map into the array function. Does that make sense? Right? So now we can do map and map and map over and over again, and we're not making a bunch of intermediary arrays. We're adding the computations sort of together in a bunch of lambdas. Okay? And so similarly, we can define zip with, which is what pull with 2 arguments is called in Haskell. Right? So another fun thing is we can generate an array from a function, right? Which is sort of how we define pull anyway, right? So we can also define fold, right? So one way we might do folding here is, right, we just use the built-in /fold in racket, right, walks through the range from 0 to the length of the array, and calls our f function here on this g of I with the accumulator, right? So we can define fold. One thing that the fold is going to do is it's going to return a singular value, right? So imagine what would happen if we created an array with pull generate, and then folded over it with pull fold. Right? There's no array actually in memory at any point in that computation. It's kind of cool, right? We can also define sum down here by essentially doing pull fold plus 0 over the array, and it does in fact sum the array as you expect it to. So what about concatenating 2 arrays? Right? Well, that's straightforward to define on this data structure. Right? We use matchlet and racket. I can pull out these 2 arrays, destructure them. And then we can create a new function that has this conditional that says, well, if the index is less than the length of the first array, then we look it up in the first array. Otherwise, we do a little bit of index arithmetic and look it up in the second array. So this works, but this is a little bit unfortunate, right? If we want fast array computations, we don't want a conditional in the middle of all of our operations on the array. Right? If you're writing this in C or something, that's not how you do this. You don't want to have to do this index arithmetic all the time. So it turns out we can use something called push arrays for that. So push arrays are basically the inverse of pull arrays. Right? So the idea is instead of having the function take in the index and give you the value, the function takes in a function that knows how to write an array. So it's parameterized over how you write the array, not how you read from it. Right? So to give an example here, compute push, this breaks open the push array, binds this function f, and then the thing that we apply f to is this function lambda ia that does vector set via. So we pass in a function that says, okay, give me the index and the array, or the value rather, and I'll write it to that vector. Does that make sense? A little bit weird. Okay, and it's straightforward to convert from a pull to a push. And in fact, we can do this without allocating anything. Right? So now we can write push concat like this. Right? So we do the same thing as we did before. We break open our two arrays. Right? Now, in this new function, right, first we call f1 with w, and then we call f2 with this function that does the index computation here. So this will first write out the first array, and then it will write out the second. Does that make sense? And there's no condition. It's just ordinary sequencing of function calls. All right. Similarly here, what if we wanted to take an array like 1, 2, 3, 4, 5 and turn it into 1, 1, 2, 2, 3, 3, 4, 4, 5, 5? Right? Well, we can do that with this push dupe function, which again calls this w function twice in a row. First time doing index times 2, and the other time doing index times 2 plus 1. Okay, so to read a little bit more about this, you can look up the big library that pushed this idea of pull arrays. It's called REPA in Haskell. The sort of modern place to look for this is in the data.array.polarize library or module in the linear base, and also in Obsidian, just an EDSL for CUDA programming. This stuff sort of originated with some of the people at Chalmers. I learned about it from Joel Svensson. And as far as I know, this has not been, at least widely popularized outside this little bubble of array programming in Haskell. So I decided to try to write a as simple a version of it as I could in Scheme. So hopefully you learned something from it.